Hello and good morning. So my name is Byron. I'm from Boston University, and I'm going to talk to you about the work that we're doing for an initiative we've started called the Unlock Project. So briefly, I'm going to talk briefly about what it is that we're doing, why we're doing it, discuss what brain-computer interfaces are, and give you some examples, and specifically the kind that we're currently working with for this project. Go into some detail about what Unlock is and how we put it together, and then demonstrate a few, or give you some examples of what we have already started working with. So we're interested in individuals who have something called locked-in syndrome, which is a profound disability. These are people who have almost no voluntary motor ability whatsoever. They can't speak. They have almost no communication ability. Maybe they can move their eyes. Maybe they can blink. Maybe they have very, very, very slow motion. That's about it. This is usually caused from a number of things. It could be advanced ALS. It could be a brain injury or stroke. But in general, these individuals are almost totally incapable of communicating. So the way we try to help them is something called a brain-computer interface. So this allows us to try and infer from their brain signals. So while they can't move, they are still very much cognizant. And so this, as you can imagine, is kind of a frightening position to be in. It'd be like, say, being buried alive or something. You can't move, you can't do anything, but you can still think, you're still aware. You can still feel things like pain. So we want to help them communicate in some way and improve their quality of life. So the Unlock Project takes this BCI technology, which so far has largely remained inside the research lab. We're trying to understand how we can extract signals from brain waves, but it's still in the research area. So people come in, they do the subjects, they do the studies, and then they go home. And we want to take that information, the research we have, and get it out of the lab into the home so they can actually use this in their natural environment. We want to do this in a low-cost way, and we want it to be portable. So if they are in a wheelchair, or they're moving around, or they're caregivers, they can take this with them. They can go to their physician or wherever they go, and they can have this available. And we want to be able to have non-experts develop applications, user applications, something like a television remote, a music player, something that people can develop who don't need to know anything about the underlying techniques in acquiring these signals or translating them into intent. So briefly, brain-computer interfaces all do three things. You have to acquire a signal of some kind. You have to decode what the intent is. You have to find a correlate from a user action or a thought process. And then you have to translate that into some actual action, such as a cursor movement. So I'm going to show a very brief movie just to set this up so you have a context over what's going on. So this is an example where a user is looking at a screen. They're driving a robot around. And they are attending to these flickering images. This is a particular style of BCI, which I'm going to talk about in a minute. But that should give you an idea to frame what I'm going to talk about next. So getting this data has a certain number of invasiveness issues. This is, how traumatic is it to actually acquire this information? So at the core, we have very, very invasive. We stick wires directly into the brain. This is done in a couple cases. Maybe you saw recently there was a woman who was able to control a robotic arm using implanted electrodes and get a sip of coffee. Very, very few people have these. Mostly these are done in animal models. They're very hard to work with. They require a lot of approval. They're rare. So it's hard for people to just get access to this. The next level, slightly less invasive, but still pretty invasive, is something called ECOG, where you take electrodes and you put them on the surface of the brain. This is actually largely used for doing things like epilepsy studies, so kind of like the figure you saw earlier, where we record neural activity, and the idea is you try to localize, say, seizure. You can also use this to do brain-machine interface, brain-computer interface techniques. Finally, there's EEG. This is where you actually put a cap on the head and you detect from the surface of the scalp. And that's what you saw in the previous video. Someone was wearing the headset with electrodes in it. So EEG stands for electroencephalography. Again, it's just electrodes on the scalp. It measures local neural population firing activity over the electrode. But unlike the other two, which require a craniotomy, surgery where you're actually inside the head, this is on the skull, and the skull really severely attenuates and diffuses these signals. So it's nice because it's really easy to work with in the sense that it's not invasive, it's easy to get subjects, it doesn't require surgery, but the signal-to-noise ratio of the kind of data you're working with is not so hot, so it becomes difficult to work with. And to give you an example, this is a much more broad EEG trace. This is from 3 channels over visual cortex, O1, O2, and OZ. And we have to figure out, using this information, the user's trying to do something. So how do we do that? So EEG has 3 main BCI applications. One is P300. This is an event-related potential. We just, you look for something, say, like you observe something that you're interested in, and we can see an activity, something that looks like this large deflection on the left, although that's actually a motion artifact. Motor imagery, where you imagine doing something like clenching a fist. So people who can't move can still imagine moving, and in some cases we're able to pick this up, detect it, and translate that into, say, a left-right motion. And finally, something called steady-state visually evoked potentials, or SSVEP. This is where you, like you saw in the video, we flicker stimuli at a fixed rate, and we can detect the frequency of the box that you're looking at and then translate it into something. So we use this because it's the easiest to work with, I would say. It requires almost no training on the user's part. It's very stable across users, unlike the others, which require a lot of training, and some users can't even do them. And it only needs a few electrodes. So we can get by with 2 or 3 electrodes placed over the visual cortex, which is the back of the head. And that's pretty much all you need. So going from this to something useful, a common approach is something called harmonic sum decision for SSVEP. So like I said, we can detect the frequency of a box you attend to, and it's actually, in a sense, as simple as taking that time series data, doing an FFT on it, and looking at the power spectra. So if we know that we have checkerboards flickering at 12, 13, 14, and 15 hertz, we just look at the power centered around those frequencies and their harmonics, and then we figure out which one has the most power, and that's the one we think you're looking at. So we have to translate it into some sort of action. So this is an example of a cursor movement task where the user has to move the light box to the green box. They can do this by attending to one of the 4 checkerboards. This will move the white box or the light blue box in one square in the direction that they attend to. And then once they reach the target, they need to indicate that they've reached it, so they do that via a selection. And in this case, we use an additional method, either an eye blink, where we can detect eye blinks using an electrode placed near the eye, or we can use something called an alpha wave. Alpha wave is a 10 hertz signal that appears almost immediately after you close your eyes. So it's a very robust signal. In fact, it's something we use as a diagnostic check to see if our electrodes are hooked up properly. So unlock. How do we take all this and how do we get it into a system that people can use? So again, our goal is to get this research out of the lab, get it so people can use it. We need this to be modular so that we can develop apps and people can use them. We want minimal licensing and cost restrictions. This needs to be cheap, or at least it has to be as affordable as possible to get it outside the lab, because individuals cannot necessarily afford a lot of software, or especially the EEG setups. It needs to be deployable. It needs to minimize the development friction. We're targeting both domain experts, so people who have a psychology background, a neuroscience background, maybe they know MATLAB, kind of, and that's about it, or motivated developers like maybe you, who are interested in helping out, know Python really well, but don't really know anything about understanding or acquiring these brain signals and decoding them. So there's a couple different BCI platforms out there. They're written either in MATLAB and Simulink, LabVIEW, C++, or Python, and really the only one of these that meets all of these criteria is Python, and so that's why we chose it. So the framework itself is set up in sort of this general structure. We are using, for display purposes, this is all right now OpenGL, so we're using Piglet. And that this viewport is this Piglet process. On top of this is a controller that handles communication and app management. Communication, we go from acquisition. The acquisition piece is just something where you're acquiring data, you're running it through some sort of decoding process, you are then shipping this over a network connection to a decision listener, a selection listener, and a raw data listener. The controller then passes this information on to any number of apps. So we can have one single app, we can have a number of apps running concurrently. The apps can switch around, so if you need to move between screens, for instance, there's support for that. And then each app has its own sort of screen object associated with it, so you can define where in the screen the app belongs. And that also abstracts a lot of the issues with Piglet so that you don't, as a developer, need to worry about Piglet if you don't want to. You can just say, I want text, draw text, and text appears, and you don't have to worry about anything like that, and I'll show an example of that in a minute. So again, like I said, we're using Piglet. We allow you to define a number of app space areas. So if you want to use the whole screen, you can. If you want to do, like we've seen, this four-choice SSVEP option, you can use the full screen with the borders for the flickering stimuli, and then define a thing area inside. This simply makes it easy to define where the apps go, so people don't have to worry about doing a lot of the translation and the positioning of everything. It will automatically position things for you based off where you've defined your apps, and it will scale it so that if you want to, say, have a full screen time scope, like we saw earlier with the EEG data, you can, or if you want it to just be in a quadrant, you can do that as well. All right, so with a simple example, this is the easiest application that you can create. You simply extend the unlock application, you give it a name, you initialize it, and we draw some text. And it's simply just giving it the text, and we want to center it on the screen. And we have to define this update function, which gets the timestamp from the last call, and whether a decision was received and whether a selection was received. Additionally, to launch the whole application, we have a runtime script. This simply is where you define your screen space, you define your app, you then pass that in to the controller, and you start. And this is what you get. Pretty basic. So we can extend this to actually do something SSVEP related with 4 choices. So what this is effectively doing is that given a decision, which in this case is an enumerated value where 1 corresponds to the top 2 is the bottom, 3 is the left, and 4 is the right, and it will move the text around. If you do a selection, it will randomly change the color of the text. Again, here's the updated runtime script. We have to create the stimuli. We provide some default constructors for creating arbitrary rectangular stimuli for SSVEP. So you just declare the list of them, the frequency they're going to flicker at, the anchoring position of where they are, if they're rotated or not. We have a number of other things if you want to change the spatial frequency, the spatial duty cycle, and things of that, the color of the checkerboards. And then again, the stimuli are just another app. So then we launch that, and you get something that looks like this. So here we've got the 4 checkerboards, we've got the text which someone has attended to the right, so it's shifted to the right. They've done a selection, so the color has changed. And we've also drawn a box around the app space just to verify that it is separate. So how do we do the communication? Right now we're just doing raw UDP sockets. So again, there's a decision, a selection, EEG data. We package everything up in JSON. We expect JSON data. It makes it pretty easy to work with. And we do have a keyboard input debugging, so you don't have to have a data source for this. You can run it without any acquisition coming in. You can use the keyboard to replicate decisions and selections, and this makes testing very, very easy. We are looking for a more robust version to this, so right now I'm interested in 0MQ or Twisted, and if anyone has any concepts about what they prefer, what they think might be good, please talk to me later. Data acquisition. So we have two systems that we are currently working with. One is two clinical EEG applications from GTech. It's an Austrian company, and they provide something called the MobiLab. MobiLab is a portable EEG system. It allows for up to 8 channels of recording, and it makes it really nice because we can take this around, we can walk around with it, and record data. It provides a C++ API or a MATLAB or Simulink interface. So we had to write our own wrapper around it. So we have something that we call PigTech, which is a SWIG wrapper around the MobiLab C++ API. It allows us to interact and acquire data directly from within Python, which is really nice. PyMotive, which is the emotive epoch. Maybe you've heard of this. This is more of a gaming platform. It's a commercial platform. The MobiLab is about $10,000 total. The emotive is about $250 for the consumer level application. It's about $1,000 if you want to get raw EEG data off it, which we do. But we also wrote a wrap around this. These both systems have a very similar API so that we can interchange them without really having to change the core acquisition level code. So we have some applications in addition to what we've done. So on the top, this is a laser bot, as we call it. This is a remote control, a TV remote control. So that's really just an IR laser, just a very big one. And we have a very, very rudimentary interface to allow you to basically do a 2D cursor movement around a remote control and do things like enter numbers, change the channel, change the volume. There's also a mode to change the orientation of the laser itself on the right. You can kind of see we have a case of a diagnostic application where we have 4 apps actually on the screen at once, a time scope, a frequency scope, an ability to select a frequency of the display and an actual display box. And then in the bottom we have a project that I am currently working on, which is incorporating this brain-machine interface with adaptive mobile robotics. And so you saw this robot moving around in the video clip, and there's a lot of work we've been doing on this I want to talk about a little more detail. So we have a controller so that you can use this in Blender. So in the Blender game engine, using an open source package called Morse, which allows you to do robotics experiments in Blender. I had to, because Blender is in Python 3, and at least I have not found any really nice, easy ways to work with images in Python 3. I had to write my own very stupid interface to libjpeg so I could convert images, get it pulled off of Blender inside the game engine into a JPEG and ship it over the network without hitting disk so we could get some reasonable performance. And using our robot interface system called Asimov, which is also all Python based. So you can see that here we have an iRobot create with a little camera on top of it, and then the bottom is the view that what people can see, and they can drive the robot around by using, by attending to the different things, by going forward, backward, or turning to left and right. Exact same program, we just changed the namespace from coming from Blender Game Engine to the physical robot, and here they can drive it around, and it has a little robotic arm on it. Again, in this case, we're using OpenCV to grab the images. We do have access to PIL here since this is in Python 2, so we use that for doing the processing. PyRobot is a iRobot create interface tool we found. There's a Dynamixel. This is the servos for the arm. It's all in Python, and again, exact same framework from Asimov that we created. Yeah, so these are the people who helped out in both the labs. The neuroprosthesis lab is largely based on the BCI part of this, the neuromorphics lab on the robotics side. This project is pretty much entirely funded by Celeste, an NSF Foundation Science of Learning Center, and some additional support from the NIDCD. Thank you.
So